The whole point of evaluating these integrals is to find the area under a curve, which corresponds to a distance traveled over a time interval. Sometimes we're not given the integral in its setup form, and we have to do a little bit of work to get there. You can use your calculator to help you all you want with these, because you may not carry these graphs around with you in your head. With practice, you should start to think of some of them. The cube root of x looks roughly like that. Y equals 0 is a horizontal line at 0, which is the x-axis, and x equals 8 is the vertical line at 8. So these three curves together contain this area, which we know is the area under the curve, cube root of x, which I'm going to rewrite as x to the 1/3 power, from where this region starts at 0 to where it ends at 8. Okay. So we have to set the integral up ourselves, but it's not terrible to do, and we're doing this with respect to x. Again, the dx is kind of just a formality now, so we don't want to forget it, but don't really worry about it either. Just make sure you write that when you set these up. Applying the antiderivative here, we will get x to the 4/3, and then divide that by 4/3, so 3/4. From 0 to 8, and we plug in an 8, we get 3/4 times 8 to the 4/3 power. 8 to the 1/3 power, the cube root is going to be 2. 2 to the 4th power is 16. And then we would subtract 3/4 times 0 to the 4/3 power, which is nothing. So that goes away, and this gives us 12. Now, I broke my own rule. I said it's always a good idea to look at your region first and try to guesstimate about what the area would be. Now, if we do look at this, this is the point 8, 2, right? Because when you plug 8 into our function, you take the cube root, that's 2. If we were to draw a box around this box would be 2 units tall by 8 units long, which will give it an area of 16. And the actual region takes up a little more than half of that box. Well, 12 is a little more than half of 16, so I'm pretty happy with 12 for an answer. I could also plug this in the calculator and do it that way. Secant squared from y equals 0, x equals 0, and x equals pi over 3. You probably don't remember what secant squared looks like as a graph. I didn't. I had to look it up. It kind of looks like a parabola, except it's bounded between some vertical asymptotes there. Hits the y-axis at 1. The line y equals 0 is our x-axis. X equals 0 is the y-axis. X equals pi over 3 is a vertical line there that will intersect our graph. If we want to approximate, this is kind of like a rectangle with a width of 1, approximately 1. Pi over 3 is just a little bit more than 1. And a height of 1 on this side, and I don't even know what on that side. But you know what? I'm going to say I know that that square is roughly 1, so I'm going to expect something between 1 and 2 out of this. Just as a guess. It's the area under secant squared, so integral secant squared x dx from 0 to pi over 3. Right. The antiderivative of secant squared is one of the ones you should have memorized. That's just tangent from 0 to pi over 3. So that's going to be tan of pi over 3 minus tan of 0. If you remember what tangent represents, tangent is the slope. So if I've got an angle of 0, that's got a slope of 0, so that part's nothing. If I've got an angle of pi over 3, that slope is greater than 1. Pi over 4 would have a slope of 1, and if you remember what the values were, the one that was greater than 1 was square root of 3. So the tangent of pi over 3 is just square root of 3, which is 1.732, which is very comfortably between 1 and 2. So I'm very happy with that answer. I hope you are too.